right, we can get started now. Is this working? Can you hear me? It's good in the back? Okay. So let's get started. It's another week, another lecture of digital circuits. So hopefully you're ready. So we're going to have more fun. Thank you very much. So today we have an aggressive agenda. We're a little bit behind because I gave you too many stories of real designs and real life. I'll keep doing that because I think it's really important for you to get the real designs in life. But we're going to wrap up the computer architecture mysteries lectures. We were talking about Bloom filters, if you remember. And I'll remind you again that this is a data structure that you will see more and more in the future as data becomes really, really big in the systems. You'll have a lot more data and you will need to quickly query the data. And Bloom filters are very much used in both hardware as well as software to quickly query presence of some element in a set, as we've discussed. And then I will do something odd. This is lecture 5, but we will talk about course logistics in lecture 5, since apparently you're here, you like the course and you want to take it. So we'll very briefly cover that, but most of the slides will be available online. And then we'll jump into the real basics. We'll start with the lowest level of the transformation hierarchy, start talking about devices, and then start building up combinational logic circuits. And then the course will be all about building up all the way into the microarchitecture, ISA, ... Okay, so I'll give you assignments. So this is one assignment. We don't have time to cover it, but I'll give you a required lecture video on why is computer architecture important. This will be fun. This will be relatively easy. Why is it important? And it's really a lecture video that I delivered at ETH when I started last year. This is in May 2017. So this is your assignment. It's required, so I'll expect you to understand the concepts. But there's an optional assignment also, which is always good to do. This is not required. Basically, write a summary of the lecture. Watch it. It's only 45 minutes. What are your key takeaways? What did you learn? What did you like or dislike? And you can submit this as a PDF or a text or an email to the Digital Technique email list. Sounds good? It'll be fun. We won't have time to cover this in the lecture. I would love to, but we have only 24 lectures, and there's so much material in this immense area. Okay, so required readings. This is just to give you a heads up. We're going to cover combinational logic and hopefully finish Verilog tomorrow. So hopefully you're doing these readings. And next week, we're going to cover sequential logic and, again, hardware description language of Verilog in sequential logic. So make sure, basically, you're done with chapters 1 to 3 in Pat and Patel book, and Pat and Patel book is this book over here. So there's a new edition coming up, hopefully, in the future. And the other book. These two books are relatively complementary. Even though they cover similar concepts, they're not exactly the same. And different people here have different styles of learning. I would recommend you do both. But if you're happy with one, and some of them don't exist, some of the topics don't exist in both books, as you can see over here. For example, hardware description language and Verilog doesn't exist in this particular book, but it exists in the other book. And later we will come to lectures where the topic that we cover doesn't exist in any of the books, actually, in the way we're going to cover it, because sometimes books become older than the field moves faster. So you're really going to learn the cutting edge of computer architecture and digital design. Okay, so let's go back to Bloom filters. I want to finish up the thoughts we had over here. Recall that we were talking about approximate set membership. I'm going to go through this relatively quickly to jog your memory. Basically, suppose that you want to find out whether an element belongs to a set, and you can tolerate some mistakes, some errors. Basically, mistake is a false positive. The element is actually not in the set, but you're incorrectly told that it is. You're fine with this. If you're fine with this, but you're not fine with this other type of mistake, which is a false but negative, the element is actually in the set, but you are incorrectly told that it's not. Then Bloom filter is a good structure because it can give you false positives, but it never gives you false negatives. So we saw that there was an example task. If you want to actually recall some mobile phones, and you want to quickly identify all mobile phone Model X owners among all possible people in the world, how do you represent this set? 1 bit per person is too much, right? That's a lot of bits. So basically, we've already gone over this, so I'm going to go over this quickly. Basically, you can reduce the set. You can represent the set with a much smaller number of bits. using a Bloom filter. And I've given you on the blackboard what's a Bloom filter, so I'm not going to go over this relatively quickly. I'm not going to go over this again. You should watch the lecture if you don't remember at this point. But as we said, you could apply this idea anywhere where this problem, where the constraints of the problem are as I described. You can tolerate false positives, but cannot tolerate false negatives. And here row population is another example. Basically, you want to refresh some of them frequently, and you want to figure out which ones to refresh. You can tolerate false positives here, because if you refresh something, even though you're not supposed to refresh it, it's fine. It just keeps the row better, right? Keeps the row active. You just waste some energy. But the other way around, you cannot tolerate. If you're supposed to refresh something frequently, and if you have a data structure that tells you, oh, this is not supposed to be refreshed, that's bad, that's a false negative. But you can actually tolerate that. You don't have that problem with Bloom filters. Okay, I'm going through this relatively quickly because we already talked about this. Basically, it's a probabilistic data structure that compactly represents set membership. What is a set membership? Presence or absence of an element in a set. What does probabilistic mean? Basically, non-probabilistic means non-approximate. You can use 1 bit per element. You're exact, basically. You can exactly determine whether an element is absent or present in the set. That's perfect information. But perfect information usually comes at the cost of a lot of storage, as we've seen in the past. And there are many ways of representing perfect information. This is one example. 1 bit per person, let's say, 1 bit per row. You could also have perfect information by storing a data structure, let's say linked list of IDs of the rows, right? Basically, all million people, the IDs, the pointers, essentially, let's say the IDs of the people who own this mobile phone X, right? And that has some storage cost also, because you need some number of bits to represent those people. Whereas if you're approximate, you can actually play tricks. You can use a much smaller number of bits and indicate each element's presence or absence with a subset of those bits. Basically, some elements map to the bits, other elements also map to. We saw that, and this is a false positive. And you can do multiple operations. Remember that we inserted into the filter. We tested whether or not something is present into the filter, or you could remove all elements. We haven't talked about remove all elements. Now it turns out, because this is approximate, removing a particular element is not easy. Whenever you remove one element, you may actually remove other elements also, because it's not perfect, remember? You're removing some bit. That bit may also map to some other element that you've inserted. Okay, think about that. So let's take a look at the operation of a Bloom filter. Remember in the board, I talked about you have a row address, and it goes to a hash function, and a hash function can be as simple as look at the bottom, some number of bits. And then if you want to insert something, you go through a hash function, and you get the bits, you get the index of the bit in this bit vector, Bloom filter, and you set that bit to 1. Now, to reduce these false positives, you can actually go through multiple different hash functions. And whenever you insert a row, you actually set, instead of setting only 1 bit, you set 3 bits. Essentially, you go through 3 different hash functions, row address, let's say 0. Hash function 1 gives you this bit, hash function 2 gives you this bit, hash function 3 gives you this bit, and you set all those 3 bits. That's, now you've inserted row 1 into this Bloom filter that says you should refresh row 1 frequently, right? Okay, let's insert, now what is a testing operation? Let's say you've inserted some rows, later you test whether row 1 exists. Testing operation is very simple. You go through you take the address of the row, you basically go through the same hash functions, and because these are the same hash functions, they will map to the same bits, and you basically test if all those bits are 1. If all those bits are 1, that means that row 1 is present, or the Bloom filter tells you that row 1 is present. Because when you inserted row 1, you set those bits, right? When you're querying later in the future, you basically query it. So if someone buys a mobile phone Model X, you record their ID, you go through these hash functions, and you set the bits associated with that ID. And later, if you want to figure out whether that someone actually has a mobile phone, you go through the same hash functions using that ID, and basically check the bits. If all of them are set, you get a 1, and that 1 tells you, okay, so that person has the mobile phone X. Make sense? Hopefully this is a simple concept. But this is a very powerful concept. So let's insert something else. Let's check something else. So remember, we inserted row 1. We did not insert row 2. Let's check if row 2 is present. Row 2, you take row address 2, you go through the same hash functions. And this hash function gives you this index where the bit is 0. This hash function happens to give you this index where the bit is 1. This hash function gives you this index where the bit is 0. And you AND those bits, meaning that all of them have to be 1 for the Bloom filter to tell you that row 2 is present. But as you can see, only one of the bits is 1. That means that the Bloom filter is going to tell you, you did not insert row 2 into me before. Right? And that is correct in this case, right? You don't get a false positive. But remember, if you, the beauty of having these 3 different hash functions is you reduce the probability of this false positive. False positive is also called a collision sometimes. If you only had hash function 2, this would be a false positive, right? Because row 1 address, when you inserted it, you would set this bit. When you inserted row 1, you would set only this bit. When you inserted row, well, you didn't insert row 2. When you checked whether row 2 is present, you would go through this hash function and you would map to the bit that the insertion of row 1 actually set. So you would get a false positive if you only had this single hash function. That's why you have multiple hash functions, to increase your confidence that you've actually inserted a particular element. The probability of collision reduces. Okay, let's insert row 4. You can have fun with it, basically. Row 4 goes through, again, you go through, you take the ID of row 4, address row 4 in bits, binary. You go through 3 different hash functions, and it turns out the hash functions map to these bits, so you set these bits. Sounds good, right? Now we've inserted row 1 and row 4. Now let's check if row 5 is present. You go through the same hash functions. Remember, we never inserted row 5. It turns out the bits that row 5 mapped to through these hash functions were all set to 1. Now you get a false positive, right? Even though you used 3 hash functions, somehow you got a false positive. The Bloom filter tells you row 5 is present, even though we never inserted row 5 into the Bloom filter. Too bad. Well, why did this happen? Because this insertion of row 4 set these 2 bits, and insertion of something else, which was row 1, I think. Yeah, row 1 set this bit, and row 5 happened to map to these 3 bits that were set by 2 different rows when they were inserted. So you get a false positive. Basically, the mobile you're checking whether this random person in the world with an ID owns mobile phone X, and this Bloom filter tells you, yes, they do own, even though they actually never purchased mobile phone X. Right? And you can tolerate it. Again, remember, if you're recalling or if you're sending a replacement mobile phone X, that person will be happy. Right? Okay, so there are problems where this actually is very, very relevant today. This is a relatively old paper, so if you're really interested, you should read this paper. It was written in 1970 by Burton Bloom, and it's essentially dealing with what we just discussed. And you can see that space-time trade-offs with allowable errors, right? Okay, I'm not going to go through this. You can read it. So let's talk about, so this course is about trade-offs and advantages and disadvantages, and anything in the world, actually, but especially in the design of systems, have advantages and disadvantages. Let's go through the advantages and disadvantages of Bloom filters. The first thing, hopefully it's obvious by now, is you get a storage-efficient representation of set membership. As opposed to using 8 billion bits, we're going to use maybe 1,000 bits, right? Much smaller. Insertion and testing for set membership are fast because the storage is small, right? You go through a hash function and you check some bits and you compare, as opposed to going through a huge list or going through a huge bit vector. You have a much smaller bit vector now. Makes sense, right? No false negatives, so that's good. If you want this in your problem. If Bloom filter says an element is not present in the set, the element must not have been inserted, right? So it's correct in terms of false negatives. And now you enable some trade-offs. That's the beauty of this Bloom filter, basically. What are the trade-offs? It's actually a complicated trade-off space. Time, in terms of how quickly you can check whether something is present or absent. Storage efficiency, how big is your bit vector. And false positive rate. So basically, if you want to reduce the false positive rate, you may want to increase the bit vector size. So that goes against your storage efficiency. That goes against your time. Or you may want to add more hash functions that may go against your time, but that may actually keep your storage efficiency. So you can actually do trade-offs between these 3 different things. And if you have a lot of data, this trade-off becomes very, very important. Actually, a lot of the search engines that you see today or use today use Bloom filters relatively heavily, but we're not going to get into that. So the disadvantage of the Bloom filter approach is you have false positives. Basically, an element may be deemed to be present in the set by the Bloom filter, even though it was never inserted. So that's the disadvantage. Now, if you can tolerate this very well, usually applications have different false positives rates they can tolerate. So you really want to size these structures based on the false positive rates you can tolerate. Again, if you're sending replacement phones to someone, maybe you have a budget in terms of how many extra replacement phones you can send, right? Then you set your false positive rate and your filter based on that. So it's not the right data structure when you cannot tolerate false positives. There are some problems where you have to be exact. You cannot be approximate. Then it's not the right data structure for you. Okay, so let's take a look at benefits of Bloom filters as refresh rate bins. Remember, we were talking about the refresh problem. There are some rows that require refreshing very often. There are some rows that don't require refreshing very often. And if you categorize them into two groups, the set of rows that require refreshing very often is very small, as we discussed in the last lecture. Now, if you use Bloom filters, false positives are fine, because a row may be declared present in the Bloom filter even if it was never inserted. This is actually okay, because it just forces you to refresh some rows more frequently than needed, right? As I said before. No false negatives, rows are never refreshed less frequently than needed, so there's no correctness problem, because you have to refresh some rows very often, as we discussed. It's also scalable. Now, let me tell you what scalable means. Basically, if you have a fixed size table, and if you want to add more elements to it, maybe you cannot insert more elements because your table is fixed size. Don't think about 1 bit per every possible element. But what if you had 1 bit for, I don't know, 1,000 elements? And you were not using the Bloom filter approach. You were trying to exactly represent the set. So that overflows. Basically, you don't have enough bits to, let's do it that way. Let's do it this way. Let's say you assign 1 bit per the address that needs to be refreshed very often. And you say, okay, there are 1,000 of these only. And you want to represent them exactly. If you have less than 1,000 of these, then that's fine. But if you actually figure out that you need to represent 10,000 of these, now you have a problem because you size your data structure to be only 1,000 entries, right? That's not scalable. You have a fixed size. Whereas Bloom filter, even if you have only 1,000 bits, you could keep inserting things, right? You keep inserting and it maintains these above properties, but at the expense of false positive rate. Does that make sense? Let's say we said only 1,000 bits and we keep inserting. At some point, probably all your bits become 1. Now your false positive rate probably goes to 100%. Meaning Bloom filter always tells you, yes, I have the element. Yes, I have the element. Yes, I have the element. So that's probably not a very useful filter, right? Actually, it's a useless filter. You might as well get rid of the filter at that point in time, right? So, but it's scalable. It still maintains these properties. It's not wrong, right? That's important in design, actually. Today, designs are getting so complicated that if you have a fixed size thing, and if it overflows, that could actually cause problems, because you can actually be incorrect. But if you have something like this, then you're not going to be wrong. It may not be useful, but you won't be wrong. Okay, and it's efficient. Basically, no need to store information on a per row basis. You get simple hardware. So you get very little hardware cost for a large DRAM system. And as I said, you should take a look at the paper if you're really, really interested in the details. Okay, and that's the paper, basically. But again, this is not required reading. This is really for the interested folks out there. Okay, any questions? Does this sound cool? No? Okay, yeah.
Well, you said having more hash function reduces the chances of false positive, but then it has more bits. So you need to use more memory, but you said that using more hash functions reduces.
That's right, exactly. So there's a trade-off over there also, exactly. And also the quality of the hash function matters. And people don't necessarily use just the bottom 3 bits, because that may not be very good quality, right? You actually randomize the index a little bit, but we're not going to talk about that here. Okay. Any other burning questions? Okay. Let me know if you use Bloom filters soon or at any time. I hope this is going to be useful in your lifetime. Okay, so this is what we've covered, basically. We've covered 4 mysteries. And hopefully you remember them. I'm not going to talk about that at this point. But let's do some takeaways. Basically, the big takeaway is it's really an exciting time to be understanding and designing computing platforms today. And there are many, many challenging and exciting problems in platform design. And we've covered actually 4 of them, but there are many, many more. And we don't have time to cover them clearly. And the interesting thing is no one has really thought about them or tackled them before, right? No one has really figured out, no one has really thought about Meltdown and Spectre, for example, in the past, Rowhammer in the past. But now these problems are coming up. And these can actually huge impact on the world's future, as you may have read about anywhere. And the reason these are happening is this is actually driven at the top by huge hunger for data and its analysis, new applications, even greater realism. So we want actually much more powerful processors underneath, right? So we can actually easily collect more data than we can analyze and understand today. Genomics is a really nice example of this. Again, I don't have time to cover it, but you can watch the inaugural lecture that I mentioned earlier as a required video. And also at the technology layer, this is the application layer, top, right? Basically, what problems we're trying to solve over here. Maybe ever greater realism is a problem, right? How do you have telepresence? It's going to be like, how does a doctor, for example, perform a surgery very, very remotely? And people can see that doctor as if he's operating, or he or she is operating at that surgery point, even though he or she is really, really far away, right? So how do you do that? But also at the bottom there, these are driven by significant difficulties in keeping up with the hunger at the technology layer. So technology layer actually changes. If you really want to have, we'll see very soon that maybe 5 billion transistors on a chip. And you really want to have 5 billion transistors on a chip because you want to do some of these real big things. Then you have problems like energy, reliability, complexity, security, safety. So that's why it's really exciting to do all of these today. And again, I'll very quickly talk about the course logistics. We're transitioning into that right now. We have increasingly demanding applications, and as early as the processor has begun, people have said, why do we need a more powerful processor? Right. You may have heard of the famous saying, why does anyone need more than 640 kilobytes of memory? Right. I won't attribute it to anyone, but today we have terabytes and terabytes, actually petabytes, exabytes of memory. Right, and we still need more. So basically, what I'll say over here is, as long as people are dreaming, applications will come. And basically, as applications push boundaries, computing platforms will become increasingly strained. So designing these platforms efficiently will become more important. And this is one dream, as I showed you in an earlier lecture, right? This may not be unreasonable. I don't know, maybe 50 years from now. How do you make it happen? I don't know. Well, maybe this is the one that's driving the car over here, right? Okay, yeah, and this was probably not, so people have dreamt of such things when they wrote books as early as 1800s, right? For example, a big dreamer was Jules Verne, who actually wrote books talking about traveling around the world, and later people actually did that, right? Other people dreamt even more. So we are able to do these things today. Okay, let's look at the technology layer. I'll give you some examples. You'll see this more in the inaugural lecture a little bit. But at the technology layer, we have increasingly diverging and complex trade-offs as well. I'll give you one example. Energy is really, really important today. This is a chip over here. Basically, you don't need to understand everything here, but let's take a look at this thing. This thing is 64-bit double precision floating point operation. Basically, it's a complex addition. 64 bits. It consumes about 20 picojoules. Maybe you don't understand what a picojoule is, that's okay. But let's look at the relative. This is a memory access. A memory access consumes about 16 nanojoules. So that's essentially about 1,000 times the energy consumption of this complex addition. So we have this diverging trade-off right now. If you want to do an add operation, if you want to add 2 64 bits, we will see more of that later on, do you actually need to bring all of them all the way here and consume 1,000 times more energy, 3 times, to bring the source operand 1, source operand 2, and write back the results to memory? That's a key question, right? So this is really cheap, this is really expensive. How do you design a system that's actually energy efficient in the presence of this? And I actually didn't tell you how much energy it takes to go to the disk. It's much larger than this. So think about it. Basically, and also there's a pass system, so the systems are increasingly complex. This was a relatively fast system, even though it may be early. It may look like today's system, but today's systems are actually much more complex. What we have today is not just a CPU. We have these heterogeneous things, like a multi-core CPU, some other multi-core CPU, FPGAs, GPU, and they're all connected together somehow, maybe on the same chip. Sometimes these are on the same chip. And they share memory, and memory is different, so it's hybrid. It can be DRAM plus some non-volatile memory over here. And they also access solid-state drives. And this is just part of the complexity, because clearly I didn't show you the accelerators over here, right? This has a lot of accelerators. Okay, so basically things are increasingly complex. So my big goal in this course is enable you to understand how a processor works, principles and precedents. You'll implement in the lab a simple microprocessor. And again, as you will see, you need to understand how decisions made in hardware affect the software programmer as well as the hardware designer. Hopefully you'll think critically. This is really important, I think, especially going into the future. Think broadly across the levels of transformation, and understand how to analyze and make trade-offs in design. So that's the reason I gave you all of these examples so far, because I think they show a lot of these things at the same time, hopefully. Okay, so I think let's go into course info and logistics. This is going to be a really fast coverage of slides because I'm not really going to cover them. But I'll introduce myself and the TAs, the team a little bit. So I'm a professor over here. Officially, I really started in May 2016. And this is the second time we're teaching this course. I was at Carnegie Mellon University before. And if you want to learn about my experience, let me know. But basically, I got my PhD from UT Austin in 2006, and then started the computer architecture group at Microsoft Research. And we looked at a lot of really, really interesting things. The memory performance attacks that I described is actually based on the work that we've done at Microsoft Research. And then I worked quite a bit at Intel and AMD, looking at their next generation processor designs, even before that actually, during graduate school, and after that too. And more recently, I worked at Google and VMware on multiple different things, on their memory systems and infrastructure, Okay, so you can find more on my website. You can reach me by email. You can use my ETH email too, that's fine. And also, if you want to meet me, you need to make an appointment, so email me, please. And if you actually email Juan as well, that would be better. Okay, so I do research and teaching clearly in computer architecture, computer systems, bioinformatics, and memory and storage systems, hardware security, fault tolerance, hardware-software cooperation. So everything that we talked about and more. So hopefully this gives you an idea of who I am. And if you're interested in any of this, I'd love to get your opinions at some point. Okay, so these are assistants. So you see Juan over there. So he's the head assistant. There's Hassan. I called him the vice head. He's sitting in the back, but he's essentially responsible for the labs especially, but he's really involved in everything in the course. And I have other key assistants and guest lecturers. I don't know, they're sprinkled around. Arash over here, Jeremy, Minesh, and Girai. So you should get to meet them, hopefully. And we have also other PhD assistants who may or may not be here. Aritra, Danielle, David, Francois, Myrdoa, and Patrick. So you will get to meet them in the labs. And we have even more assistants, given that there are 400 of you. But you should get to meet them because they're going to be attending your labs. These, almost all of them are folks who have taken this course in the past and they've done well. And some of them have been actually TAing, being a student assistant for a long time. Okay, and you can look at the schedule online, basically. Hopefully you're signed up for labs, right? Good. Okay, so if you need help, hopefully you know that you should post your question on Moodle. This is really the preferred forum, especially for technical questions. You should post that so that we can help you better. Or write an email to this email list, but email is usually more cumbersome. So unless you have a really personal question, for example, I would suggest not writing to this email list. Okay, and where do you get up-to-date course info? Hopefully you saw this website already. And this is your single point of access to all resources. We put up, for example, an optional homework assignment. There are no homeworks in this course because we don't grade them, but we will put optional homework assignments so that they help you understand the material. Okay, so I'm going to go through this relatively quickly because hopefully you know all of this, right? And if you don't, these slides are online. But I will make this comment. This course might seem like only computer hardware, but hopefully I've convinced you with these examples that computer hardware and software, even though they might look different, they critically affect each other today. So you will be much more capable if you master both hardware and software and the interface between them. And this is especially true going forward. Maybe there was a time in the past in the design of computers that knowing just hardware and knowing just software was okay. Maybe you would still make a lot of money that way, or you would still solve problems because problems were not as complex. But going forward, if you want to solve real problems, big problems, or if you want to make a lot of money, I don't know, everybody has different goals in life, right? It's better, I would suggest doing this basically. It's better if you know both. You can develop better software if you understand the hardware. You can design better hardware if you understand the software, and can design a better computing system if you understand both. Okay, and we already said this before. Basically, we cover the hardware-software interface and microarchitecture. We call the 4 mysteries and the transmitted story, right? Does anyone remember the transmitted story? Yes, some of you. Okay, if you don't, go to lecture 2, I think. Yeah. They set out to make a lot of money. And they actually did innovate a lot to make money, but they were not quite fully successful. Okay, what do I expect from you? I think I'll go through this relatively quickly. Basically, learn the material, work hard. I mean, obvious things that from an ETH student, right? One thing I will say, start early, do not procrastinate, because things can actually pile up quite a bit, right? We have a lot of labs. It's not an easy course, it's a fast-paced course. And I will remind you of this saying by Louis Pasteur, who said that chance favors a prepared mind. So if you really want to be successful in life, you want some chance. Chance is always good to have, right? But turns out chance is biased. If you're prepared, you can see the opportunities much better. So whenever chance comes, if you're prepared, you can take advantage of it. If you're not prepared, for example, if you don't have the background on Bloom filters, let's say, chance may come, and you may need to solve a problem, but you don't know Bloom filters, and chance passes away, right? Okay? So I think I like this saying quite a bit, and he's looking very seriously over here at you. Okay, I mean, this is hopefully clear. You'll have 9 lab assignments, and this is one of the reasons why it will be heavy, but you'll learn a lot of concepts also, so it's better to do the readings and prepare and manage your time. But hopefully, the course will not only be heavy, but it'll enable you to learn a lot of fascinating topics and understand how a microprocessor actually works from the ground up. Now, the microprocessor you will design in the labs is not going to be satisfying, I'll tell you. It's going to be very, very basic. And it's going to be related to mainly the first half of the course, let's say. We'll see a lot of other concepts later on that you just cannot have time to do in a first-year course. A lot of processing concepts, out-of-order execution, for example. We're not going to require you to do a lab on out-of-order execution, otherwise that will take a year, probably. I've done many designs of out-of-order execution, both in simulation, high-level simulation, as well as RTL. RTL is hardware description language designs, and it always takes a lot of time. So you will get a glimpse of what a microprocessor may look like. It won't be a real microprocessor, but hopefully you will enjoy it. But we will supplement it with a lot of the concepts that are employed in real microprocessors today, so that you will really, hopefully, imagine what you can do if you're actually designing microprocessors in the field. And hopefully, I think separately from this, this will change how you look at and think about designs around you. Remember the Stadelhofen? Maybe this course will help you think about it in a different way. I don't know. If it does, let me know. Okay, I'm going to skip this because this is kind of obvious, hopefully. This is all online. Okay, basically, I would recommend you to watch this, well, I will require you to watch this video to talk about computer architecture as an enabler of the future. But hopefully I've convinced you about most of this, but hopefully you'll enjoy this video. But the first step is really understanding the fundamentals, right? Without the fundamentals, as we said in the first lecture, you cannot do much. You can change the world only if you understand it well enough. This is true for everything again. Especially the basics. If you understand the basics and the fundamentals really well, you can build something on top of those. And if you understand the past and present dominant paradigms, again, you can do something more. Their advantages and shortcomings, the trade-offs, as I mentioned, these are really important. and what remains fundamental across generations. So things may change over time, like tens of years, hundreds of years, maybe thousands of years, but some things remain fundamental across those generations. So it's good to understand what those are. I mean, clearly computing is not as old as thousands of years, right? Some people argue that some aspects of computing were present in the past, but not the computing, electrical computing that we know it. So we will focus a lot on fundamentals today, and what techniques you can use and develop to solve problems. So let's take a look at some of those fundamental concepts. I'll give you a very quick overview of the lecture also. Basically, what is a computer? It really consists of three key components: computation, communication, and storage, or memory. Storage and memory can be merging sometimes. So this is a very abstract view at some abstraction level. In this course, we're going to focus a lot on the computing unit, actually. You're going to learn a lot about it. We may focus a little bit on the communication unit, but you will deal with communications like wires, buses, etc. In your designs, clearly, but we're not going to do a lot on this part. We're going to touch on the memory storage unit a little bit toward the end of the course. I mean, you're going to look at register files, for example. We're going to look at memories. We've already talked about a lot of memory-related issues early on. This is a really, really important component, but we just don't have enough time to cover a lot of it. So this course mainly focuses on this part and a little bit on this part. And basically, you will see this picture later on again when we talk about microarchitecture. I'm not going to go through this again. So let me give you a very quick overview of what you will see. I'm not going to cover all of this. Basically, we'll start with this first. I'll start with combinational logic design today, and then we'll go through this. This is relatively low level. We're going to build the basics relatively quickly. And then we're going to jump up a little bit, talk about the interface, basically instruction set architecture. We're going to focus a little bit on MIPS. MIPS is a nice architecture that's used in real systems, but it's also nice for teaching. That's why we're sticking to MIPS here. And we're going to talk about assembly programming a little bit. And then we're going to go into microarchitectures that you're going to design, basically single cycle microarchitecture. And then we're going to talk about more advanced concepts, which you may not understand right now, but we'll get to it. Okay. So let's start with the real basics. Any questions so far? I know I've gone through these really quickly, but this is hopefully really simple, and you can refer to it online. Okay, so we'll start with combinational logic, and this is what we will learn today. Basically, we'll start with the very basic building blocks, starting with transistor as our basic abstraction level. And then we'll build logic gates on top of that. And then we'll talk about Boolean algebra a little bit. Have you all studied Boolean algebra before? Who studied Boolean algebra? Okay, we're going to go through this really quickly. Who studied minimization of Boolean equations? Okay. That's interesting. A lot of you have. Who has not studied Boolean algebra? No? Should I not teach you Boolean algebra? Okay, I'll cover it. I think it's good for you to know this. Who doesn't know anything about Boolean algebra? Or, okay, who doesn't know anything about minimizing Boolean equations? Okay, that's good. So we're going to focus more on minimizing, reducing the Boolean equations. Okay, I'll give you another question. Who knows about De Morgan's laws? Okay, wow. Okay, where did you study this? In logic? Discrete math. Here? Okay, I see. Okay, I'm going to go through this quickly then. But we're going to talk about combinational logic. Who knows about combinational circuits? Okay, that's much fewer than. Who does not know about combinational logic? Okay, that's much better. Okay, good. And then we're going to talk about how to use Boolean algebra to represent combinational circuits and minimizing logic circuits if time permits. Who knows about Carnot maps? Carnot maps. K-maps. Okay, that's fewer. Who does not know about K-maps? Okay, I like that. So we're going to go through quickly. Some things. So I'm going to go through this relatively quickly. This is the board that you're going to be using, but these are microprocessors, and they're also custom ASICs, application-specific integrated circuits. These are all different types of things. This is just a table that summarizes some of them, but microprocessors are general purpose. FPGAs are configurable. You're going to program the FPGAs, ASICs are basically customize something, everything to an application. Basically, it's an application burned into hardware. You can think of it that way. So clearly, if you burn an application into hardware, it's really fast and efficient. Microprocessor is general purpose. It can execute any program you write, as long as you compile down to it. So this is slower. And FPGAs are reconfigurable. You can actually reconfigure the hardware to, so that you can map any software on the hardware in terms of logic circuits. But because of reconfigurability and flexibility, you cannot customize everything really well. So it's not as fast as the ASICs. And maybe it's not as fast as the microprocessors also. So all of these are actually used in real systems today. For example, even today, data centers incorporate FPGAs. You can rent FPGAs from Amazon and program them and execute your program online. This was not the case in the past. ASICs exists. Tensor processing unit is one example. There are many ASICs in that. And microprocessors. We're going to focus a lot more over here. So how long it takes to develop a program, you could argue, of course, right, depending on what kind of program, but this is relatively easy to program with general purpose programming languages. Here, we're going to use hardware description languages. Here, we're going to use hardware description languages also, but you do more of that to customize everything, but we're not going to look at that as much. But the principles remain the same. They are all built on transistors, 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 and you build logic gates on top of them. Okay, performance depends, of course. Here, you may not be able to execute the application you want, right? Your performance is 0, because you cannot execute. But if you're actually executing the application that you want, then the performance is really, really good over here, right? Okay, you can study this on your own, and this is not always correct. So I apologize for the other companies that may not exist here. But anyway, we're going to look at Verilog or VHDL. These are the hardware description languages. Our focus will be on Verilog because this is more commonly used, especially in real designs today. Usually companies use their own languages that are modified based on some of these. Basically, we're going to see how these work by programming these. And again, the principles are the same, right? There's no difference in principle. You can actually build a general purpose microprocessor on an FPGA, and it will be general purpose, except you need to handle the program transfer into the FPGA, of course. Okay, you'll understand that better. And we're going to use this language. We're not going to use C, C++, or Java, or Python. Sorry, we're going to use something lower level. But it's going to be very parallel compared to whatever you've seen. Actually, hardware is inherently very, very parallel because you'll see that you will need to deal with a lot of signals at the same time in a given cycle. You need to reason about the parallelism of those signals. Okay, so building blocks. Basically, we're going to start with transistors. Right? Transistors are, computers are built from very large numbers of these transistors, and it's really a MOS transistor, metal oxide semiconductor. And here's some example numbers. Pentium 4, which was the flagship microprocessor of Intel in 2000, had only 42 million transistors. Today, we have chips that have more than 3 billion. Actually, I cannot keep up with this. And I'm going to show you examples of it. So this lecture, we're going to look at how the MOS transistor, metal oxide semiconductor transistor, works as a logic element. I'm not going to go into device level details. We'll draw an abstraction layer. Otherwise, this will be a physics course. And we're going to talk about that a little bit. And then we're going to talk about how these transistors are connected to form these logic gates. We're going to go a little bit higher. And then how logic gates are interconnected to form larger units that are needed to construct a computer. So larger logic gates or more complicated logic gates that have more functions. So let's keep going. Even though you're going to hear the bell, we'll keep going for a while until we find a good logical break. Does that sound good? Okay, good. Okay, so what's a MOS transistor? Basically, a MOS transistor is formed by combining conductors, metals, that's the M, insulators, oxide, and semiconductors. That's why it's called a MOS transistor. Basically, it looks like this. Again, source, drain, you don't need to worry about. This is about conductance of electricity. And we're going to talk about the gate, and we're going to apply some voltage to the gate to control this thing. And we're going to see that if you apply some voltage to the gate, you can connect the source to the drain. As a result, you get a closed circuit. If you apply some other voltage to the gate, you get an open circuit because source and drain is not connected. Okay, why is this useful? Basically, you can combine many of these to realize simple logic gates. And the electrical properties, as I said, how are these really constructed are beyond the scope of what we want to understand in this course. They're below our lowest level of abstraction. So let's talk about the different types of transistors. There are two types of transistors that we're going to deal with, N-type and P-type, negative, positive. Basically, N-type, we're going to denote it this way, drain, source, and a gate. P-type, we're going to denote it this way. Basically, the only difference is this little dot over there. That dot will be our symbol for inversion. Essentially, you can think of it as like a knot. So this gets activated if it's inverted. That's the only difference. Basically, they both operate logically, very similar to the way wall switches work. Have you ever used a wall switch to turn on the lights? You can use it over there if you haven't. So basically, that's exactly what the principle is. So basically, if you are using a wall switch, if you go into your room, if you want to turn on the lights, you either press it or do that. You have the light bulb connected to a power supply. What you're doing with the wall switch is, essentially, when you turn it, you're closing the circuit. For this lamp to glow, the electrons must flow through the circuitry from the power supply, and you need to complete the circuit. You'll need a closed circuit, so that you create a voltage differential, right, between the one end of the power supply and the other end of the power supply. And there must be a closed circuit, basically, to supply the power, to supply the voltage to the lamp and back from the lamp to the power supply. And you can turn off or on the lamp by controlling this wall switch. That's essentially a transistor. You can think of it that way. In fact, you could build it with a transistor. But basically, when you flip it, you get a closed circuit. When you unflip it, you get an open circuit. And when you get a closed circuit, the lamp glows. Right? And that's essentially a transistor. Basically, instead of the wall switch, we could use an N-type or P-type transistor to make or break the circuit, to make it closed circuit or open circuit. So by applying a voltage to the gate, this is a schematic. We're going to draw schematics in this course. This is the N-type MOS transistor. So if the gate is supplied with high voltage, the drain gets connected to the source, and this acts like a piece of wire, continuous wire. This is true for N-type. Okay, N-type, high voltage. And of course, depending on the technology, this voltage may be different. Also, it depends on what kind of transistor it is, but we're not going to go into that in detail. For example, in flash memory, sometimes you apply much higher voltages than this one. But usually in microprocessors today, the voltages are getting lower and lower. Why? Because voltage actually affects your energy consumption quite a bit. There's this famous power law equation. Let me ask you, what is the power equation? How do you compute power? Any electrical engineers here? Yes?
Voltage times current.
Voltage times current, that's good, actually. But there's another equation if you want to compute power, but you're right. Essentially, power is related to voltage. What is current?
Current is voltage divided by resistance.
Exactly, yes. Now you're getting somewhere. Basically, voltage times voltage, right? You have voltage squared. Yes. So power is actually correlated quadratically with voltage. If you reduce voltage by half, you reduce power by 4 times, based on just what he said. If you don't know about that, that's okay, you can go and study. So there's a big push toward reducing voltage today in systems. Okay, let's go back to the transistor. So if the gate is supplied with 0 volts, not high voltage, instead of, let's say, 3 volts, we supply 0 volts over here, the connection between the source and drain is broken. It's not a piece of wire anymore. It's open circuit, so it doesn't conduct. Essentially like a wall switch, so let's take a look. Basically, we're going to use the same example, but we're going to get rid of the wall switch, replace it with this N-type transistor. Now, if we apply 0 volt to the gate with this guy, so somebody needs to do that application, that's our input. It could be a girl also. We're gender neutral over here. We're not North Carolina. Sorry. Okay, I guess I'm recorded, but that's okay. There's another story over here. There's another story over here about North Carolina, which I will not. I like North Carolina quite a bit, but maybe not some of the laws. Okay, basically, if you apply low voltage over here, what happens is you can connect. This gets disconnected. Essentially, you get an open circuit, right? It's not a closed circuit. As a result, the bulb doesn't glow. But if you apply high voltage over here, 3 volts, because of the properties of the N-type transistor, this gets connected and the bulb glows. It's essentially a wall switch, right? And this is going to be our shorthand notation. Basically, this is going to be what it will look like when it's turned on. So we have the high voltage over here, power supplies one end, and this is the other end of the power supply. This is ground, this is power. Okay, so this is the N-type transistor. The P-type transistor works exactly the opposite way. Basically, to turn on the P-type transistor, okay, so in this case, the N-type, the circuit is closed when the gate is supplied with 3 volts. If you have P-type, it's the opposite. The circuit is closed when the gate is supplied with 0 volts. That's it. And we'll see why this is useful in a little bit, actually. You need both types to build a computer. Okay, shall we take a break here? That sounds good. Okay, let's come back at 2:20. So now you know how a transistor works, at least at some abstraction level, right? This is our wall switch, and we're going to build everything on top of this. So remember, N-type and P-type transistors. N-type transistor turns on when you apply high voltage to the gate. P-type transistor turns on when you apply low voltage to the gate, of the transistor. Unfortunately, it's not the same thing as a logic gate. So here we have an unfortunate terminology. There's a gate of the transistor, but that's different from the logic gate itself. Hopefully you'll understand that. Okay, so let's build logic gates. Basically, we're going to go one level higher in the abstraction. Now that we know how a transistor works, we're going to build logic out of it. Let's move over here. Basically, we're going to build logic out of individual MOS transistors. And the logical units are called logic gates. They implement Boolean functions, which you told me that you all know about. So you will see examples of this more. So basically, we're going to make logic blocks using CMOS technology. So I'm going to throw another term at you. CMOS is complementary metal oxide semiconductor. Basically, what it means is that you use both N-type and P-type transistors. That's what it means. And we're going to look at one of the simplest logic structures that exists in a modern computer that looks like this. And basically, this is the P-type, as you can see, and this is an N-type. Remember, N-type turns on when the input has high voltage. P-type turns on when the input has low voltage. As you can see, we've constructed something over here. And this something has a power supply over here, high voltage, ground over here, low voltage. Input is connected to a P-type transistor over here, and it's also connected to an N-type transistor over here, and the transistors are connected this way, and output is drawn out from here. Now, my first question to you is, what does the circuit do? It inverts the current. Basically, it inverts the input. Now, let's take a look at how it does it. Basically, it's an inverter. It's called a NOT gate. So let's take a look at what happens when the input is connected to 0 volt. Now we have this person over here, he or she gets electrified. So basically, my native language is Turkish. I'll have to do this. Turkish is a gender-neutral language. There is no gender in Turkish, so there is no he or she. So I find it's very odd when we talk about when we have to specify gender over here. And I cannot say it to this person. Actually, Turkish is a really gender-neutral language. There's no he or she or it. If you say oh, you don't know the gender, basically. Now, clearly, I'm not going to say oh over here. But I'm going to say maybe this girl or this guy. So whatever this thing is, you apply low volt, yeah. And I'm still learning German, so hopefully you'll help me. The gender is one of the most difficult parts, actually, if you're coming from a language that doesn't have gender. Okay, basically, of course, I'm very comfortable with English, as you can probably tell. English does not have a lot of gender, but it does, as you can see over here. Okay, anyway, so basically, the first question is, what happens when the input is connected to 0 volts? When this person is electrified, the input is electrified. Well, it is not electrified. You get 0 volts. Let's take a look. Basically, this is what happens, right? As I said, let's go back over here. Well, this is the N-type, this is the P-type. The N-type acts like a closed circuit, so the ground does not get connected to the output. The P-type on the other end turns on. You get an closed circuit over here. Sorry, this is the open circuit. Basically, this gets turned off, so this gets disconnected. So the ground doesn't get connected to the output. On the other end, because this is 0 volts, on the P-type transistor, you get this transistor connected. The wire gets connected over here. As a result, it conducts. So the output gets connected to the power supply, or the power line. So it gets 3 volts in the output. So we supplied 0 volts in the input, we got 3 volts in the output. We've inverted, essentially. So P-type transistor pulls the output up, as you can see. So what if we have the input connected to 3 volts? Again, this person, now it has high voltage over here. Now exactly the opposite happens, right? This gets turned on because it's N-type. As a result, the ground gets connected to the output. But this one becomes open circuit, so the power is disconnected from the output. Now, as a result, output becomes 0. Now, we again invert it, right? So N-type transistor pulls the output down. So this is essentially our NOT gate, done in CMOS, complementary metal oxide semiconductors, P and N types together. Why is it a NOT? Essentially, you're inverting the voltage. And of course, you can assign Boolean values to the voltage. 0 volts could be 0, 3 volts could be 1. So you take 0 and invert it, it becomes 1. You take 1 and invert it, you get 0, right? So one possible interpretation in Boolean is you can interpret 0 voltage as the logical 0 value and 3 volts as logical 1 value. But this is one convention, right? It doesn't have to be this way. It can be the opposite, actually. Okay, and we write a truth table. So this is one example truth table over here. Truth table specifies for all possible combinations of input what kind of output you would get. And I show you these intermediates, what happens to the transistors over here also. And I've already gone through it, so you can actually see that when the input is 0, the P-type transistor is on, the N-type transistor is off, so you get a 1 in the output. If the input is 1, the N-type transistor is on, the P-type transistor is off, as a result, you get 0 in the output. So this is our NOT gate. And there's some mistake over here. That's not how it appears in thing. But basically, this is y equals a bar, or complement of a. That's the function we get. And it's represented this way in the logic gate terminology. This is an abstraction level. We moved from the transistor level abstraction level to this. This means this is a NOT gate. Right? And usually when you see this little circle, it's inversion. Okay, it's an inverter. And I already said, I told you what a truth table is. Truth table tells you what would be the logical output of the circuit for each possible input. And this is the simplified truth table. Actually, the previous one is not really the truth table because I gave you the intermediate states of the transistor. This is the real truth table. You have the inputs, and there's only one input, A, and there's only one output. Inputs are on the left-hand side, outputs are on the right-hand side, and you see this. This is hopefully easy. You've seen truth tables before? Okay, good. Okay, let's build more complexity. So I can ask you the question, why did we need complementary CMOS? Now you can do critical thinking over here. What if this transistor was also N-type? Would this work? It wouldn't work, right? In fact, what you would get would be garbage. Basically, if this was also N-type, if you applied, let's say, high voltage to it, the output will be connected to this 0 volts and 3 volts at the same time. What do you get? Okay, let me ask you another question, basically. What if you did not have the transistor at the bottom? You just wanted to have the thing at the top over here. And it was P-type. If you applied an input of 0 volts, this would get turned on, and output will be 3 volts, which is fine in that case. If you applied an input of 3 volts over here, this would get turned off. Now the output is not connected to 3 volts, and imagine this doesn't exist. Output is connected to nothing, right, if this didn't exist. And if the output is connected to nothing, there's really nothing that's driving the output. As a result, you don't know the value. This is usually called a floating value, as we will see in the next lecture. Basically, it's marked with a Z. You really don't know the value. So that's why we need complementary complementary transistors over here to form the NOT gate. You have to have these two things, and you have to have them p-type and n-type connected this way. Okay, if they were both n-type, there's some other problem, which is yeah, if you have both n-type, whenever you have 0 over here, what you would get over here is nothing will be turned on, right? If both were n-types, again, your output would be floating, right? Make sense? Okay, that's why we need complementary metal oxide semiconductors. Now let's build more complex gates. This is another gate over here with our person again. Now they're controlling two inputs. So what does this do? I'll ask you the question. Anybody has seen this transistor level before? Some of you, but not a lot. So anybody guessing what this does? I'll give you a second. I don't see any hands being raised. That's good. Hopefully you'll learn something. No tricks here, just electricity. Yes?
If both inputs are 1 or high voltage, you'll get a 0 voltage output, and if either of the inputs are both 0 voltage, you get a high voltage output.
Okay, so basically what you're saying, you get 0 volts in the output only if both inputs are 1. Otherwise you get 0 in the output. And that's correct actually. And this has a special name. Do you know what the name is? This, yeah. But that's not a name, as you can see, it's a picture. So we call this a NAND gate. N-A-N-D, basically, not AND. And she's absolutely right. Basically, and you can think of it this way. If both of your inputs are 1, these transistors, N-type transistors that are in series, become like a wire, and the output gets connected to 0 volts. If both of your inputs are 0, meaning 0 volts, these, well, I'm not absolutely correct because I have to look at over what's happening over here. See that output is connected to here over, basically this point and this point. Now this is a bit confusing. It's not connected to this wire over here. So this means a connection, basically. If both of our inputs are high voltage, the N-type transistors turn on, so the output gets connected to 0 volts. That's good. So we're going to get 0 volts, hopefully, unless we do some mess over here. If both of our inputs are high voltage, these get turned off, and the output does not get connected to the high voltage over here, so output is connected to low voltage when both of the inputs are 1. Now, if any of these inputs is 0, this becomes an open circuit, meaning this is not a wire anymore, so output will not get connected to 0 volts. That's the realization. But if any of these inputs are 1, it could be 1 or both. Sorry, if any of these inputs are 0, it could be this one being 0, A being 0, B being 0, or both being 0. In that case, you can see that the transistor whose input is 0 conducts, and the output gets connected to 3 volts. And it doesn't matter if this one has an input 0, or this one has an input 0 to the gate, or both have an input 0. These are parallel to each other, as you can see. Output gets connected to 3 volts if any one of these transistors is turned on. So you can see that this is a parallel circuit. These transistors are connected in parallel from the input to the output. So if either of them turns on, you get the input connected to the output. These transistors are connected in series from the input to the from the source to the output. As a result, both of the inputs need to be 1 in this case because these are N-type for this 0 volts to be connected to the output. Okay, basically what I said, I've already animated this. Let's draw the truth table over here. P1 and P2 are in parallel, only one must be on to pull up the output to 3 volts. So if any of P1 and P2 are on, which happens if either A or B are 0, you get a 1 at the end. And 1 and 2, on the other hand, are connected in series, and both must be on to pull the output to 0 volts. So this is the only case where you get a 0. Okay, so that's the truth table, basically. And this is an AND, because it's really the inversion of the AND of A and B. Right? It's the NOT of AND of A and B. That's why it's not AND, or short form is NAND. Make sense? Okay, so this is how we denote it. Basically, this is the NAND, and that's the inversion. And this is the truth table. It turns out this is a logically complete thing. Now, what does that mean? Basically, you can build any logic out of this. Just an AND gate. We're going to talk about logical completeness later on. We're going to talk about how you can build any logic out of NOT, AND, and OR. But NAND is actually sufficient to build any logic. NOR is also sufficient. Okay, so NOR, now you can imagine what NOR is, right? Not OR. Okay, so let's take a look at AND now. Well, now we have NAND. How do you build AND? Any guesses? AND truth table looks like this. It's essentially the opposite of NAND. And this is the logic description, so it doesn't have this one. This little circle over there. And this is our AND gate. It's more complicated. But basically, this is NAND. You take the output of the NAND and invert it using an inverter. And by using 6 transistors, you get an AND gate. Make sense? That's very simple. Okay. So basically, what we've learned is this. This is the NOT gate, this is the NAND gate, and this is the AND gate. This is the logic level abstraction, this is the truth table, and this is the transistor level implementation of the logic level. Actually, we started this way and went this way, but now we understand. Okay, basically, the general form used to construct any inverting logic gate is not NAND or NOR, right? This is essentially what this looks like. This is the general CMOS gate structure. You get NOT, NAND, or NOR by doing this. I didn't show you NOR, but if you can think about NOR, it's going to be the opposite of this. These transistors that are P-type will be connected in series, and these transistors that are N-type will be connected in parallel. Make sense? Then you get an OR gate. And if you want to get an OR gate, you add another inverter after that output. But your books cover this. You can take a look. Basically, what we have is you have some PMOS transistors over here, positive MOS, P-type transistors that are trying to pull up the output, pull up to the 3 volts. And you have some NMOS, N-type transistors that are trying to pull down the output to 0 volts. And you can actually build any type of logic over there as long as you connect the transistors in a nice way. You can actually build a really complex gate, which we're not going to do at the moment. But you can do transistors in series or in parallel. And when the transistors are in parallel, the network is on. If one of the transistors is on, as we've seen. When the transistors are in series, the network is on only if all transistors are on, right? And it could happen here or here. Okay. I'm not going to go into detail, but essentially you can imagine many complicated gates over here. So basically, these are our common logic gates. And to be complete, this is a buffer. Basically, the buffer is really not a logic gate, but it really amplifies the signal, which we're not going to talk about as much. The input is the same as the output, but you have an amplifier. Have you ever used sound amplifiers? You can think of it as a sound amplifier. The electrical signal is weak, you go through this thing, and that thing amplifies the signal. Maybe, for example, you lost some voltage, right? It's not exactly 3 volts at that point, it's 2.5 volts, because you're so far away from the power supply and the noise is very high, so you want to amplify it. Okay, inverter is basically the inverted version of this. And this is AND, NAND, OR, NOR. Have you guys seen the XOR function? Okay, so you know about XOR and XNOR, and you can tell me how to do it in transistors. That sounds like a good assignment. Optional. And it's already in your book, so it's not going to be hard. But I'd recommend that you do XOR and XNOR by thinking, as opposed to looking at the book and drawing the transistor level implementation of XOR and XNOR. Now, if you have one of them, it's easier, of course. The other is easier. And I would suggest starting with XNOR. It could be easier. Okay, larger gates. Basically, we can actually extend the gates to more than 2 inputs. I'm not going to go through this, but essentially, you can have 3-input AND gates as opposed to 2-input AND gates, or 10-input NOR gate. You just have more transistors to ensure that the inputs are that. So 3-input AND gates, basically, or 3-input NAND gates, will essentially add 1 more transistor to the parallel part and 1 more transistor to the series part, right? To have 3 inputs. That's it. Of course, 10-input NOR gate, you can think about it, and you can see your readings. Okay, let's do an aside very quickly. Basically, these transistors, we have, now you know how logic gates are built, but there's been an enabler of many gates on a chip, and that's what's called Moore's Law. Have you heard about Moore's Law? Okay, good. So I'm going to go through this quickly. So this is an example of Moore's Law. So it's called Moore's Law because Gordon Moore, one of the co-founders of Intel, coined the term by making some observations as early as 1960s. And the law holds even today at the moment. Basically, it says component counts on a chip double every other year. On an integrated circuit, double every year. And I say double over here. Some people say 18 months. It doesn't matter. It doubles at some relatively constant number of months. This is actually from Gordon Moore's paper from 1965. Basically, what he did was he plotted the years, he plotted the number of components per integrated function, integrated circuit, let's say, and he saw that, oh, it follows this linear curve. Well, except it's not linear, because this axis is logarithmic, it's really an exponential curve, right? Things are basically increasing exponentially. And you can actually cram these, actually his paper is titled Cramming More Components onto Integrated Circuits. Basically he said that this is happening because circuits are shrinking as a result, and the size of the transistor is shrinking. As a result, we can put more transistors in a given square millimeter, let's say, or square nanometer today. And if you read the paper, you'll see that there's a relative manufacturing cost per component, and as years pass by, this relative manufacturing cost per component reduces, and there's an optimal point. As you can see, this curve is like this. If you actually put more components per integrated circuit, at some point your cost starts increasing because your thing is too big and your yield actually becomes worse. Not all chips work after some point, and there are many other reasons as well. But over time, as you see, the costs, manufacturing cost per that component is decreasing significantly. And this is just 1962, 65, and this is his projection for 1970 at the time. But this law is quite powerful. As you can see, starting from 1971 over here, 2011, we now have about 3 billion transistors, and even this is an old picture, and you can see that the curve actually looks nice. We're fitting the picture from the paper to this picture from Wikipedia. And this is actually another one over here that goes as far as 2016. So you can see that some chips are approaching 5 billion transistors. Actually, I cannot read over here. So we're at 5 billion transistors today. What do we do with these things? Right. And this is happening because we can reduce the size of that transistor so that we can squeeze out many, 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 many more transistors on a single chip. So it all begins with that transistor. This is called the transistor scaling theory, and it's practice also. Bob Denard actually, Bob Denard is the inventor of DRAM that we were talking about, dynamic random access memory. He's been at IBM for a long time, and he came up with this theory called Denard scaling now. Essentially, you reduce the size of the transistor, you get more of them, but also reducing the size of the transistor enables you to reduce voltage and other things. So you can actually have this nice scaling theory that enables you to put many, many more components on a chip. Now, we're not going to talk about that beyond this, but this gives you why computing has been so successful. So if we weren't on this curve, that is exponential, again, I call it exponential because this is really logarithmic over here, then computing wouldn't have been so successful, right? In the end, it boils down to really, really efficient manufacturing. People are able to manufacture these transistors really efficiently. And the key question, of course, is this going to go more? And some people claim that it's not going to go more, but it seems like it's keeping on going. So we'll see. Basically, what is the fundamental limit of this? We'll have to see, and maybe you'll see it during your lifetime, I don't know. Can we make the transistor smaller than an electron? I don't know. That sounds tough, right? Something needs to flow through this transistor. Okay, that's some food for thought for you. But this is recommended reading. It's only 3 pages. It's written in a different language, but as you can see, one of the quotes over here is, with unit cost falling as the number of components per circuit rises, by 1975, economics may dictate squeezing as many as 65,000 components on a single silicon chip. That's 1975, 65,000, right? Again, we're at 5 billion today. Another quote, which is really forward-looking, I think, will it be possible to remove the heat generated by tens of thousands of components in a single silicon chip? And today, this is a big deal, actually. Heat is really important. A lot of these things are designed with a thermal design point in mind, and that thermal design point is, how can I ensure that I don't burn the person's hand, right, or head? So if you're actually thinking about putting brain-computer interfaces in someone's brain, that thermal design point is actually much, much more stringent. So you can see that this is actually really, really important. Okay, how do we keep Moore's law? I'm not going to speculate a lot, but you can read this on your own. Basically, how do we manufacture smaller transistors? Some structures are very small already. Maybe we need to develop better materials with better properties. That's not the subject of the course. You should take a materials science course for that, perhaps. And that's a lot of innovation can happen because of that. Optimizing the manufacturing steps, maybe, I don't know. New technologies, can you actually come out with new technologies? And this is really important. Maybe people should be, actually there are people working on all of these to ensure that you can cram more components onto the integrated circuit. But at some point, we may really need to transition to really, really new technologies. But we don't know, we're not there yet. Okay, hopefully this was fun. Now we'll get back to combinational logic circuits. Okay, now we can build logic circuits. Let's build some more. We understand the workings of the basic logic gates. What is our next step? Basically, we would like to build some of the logic structures that are important as components of a microarchitecture, right, of a computer. So a logic circuit is composed of inputs and outputs, and it looks like this. We're going to do some Boolean algebra, basically, but I'm going to go through it quickly because you told me that you know about it. So inputs, you have some inputs and outputs, and you have some functional specification of the logic circuit, and we will talk about timing specification also. Because if you want to run the circuit at very high frequency, you'll need some timing specification. Timing is basically how long it takes. Functional specification that describes a logical relationship between inputs and outputs. There may be many implementations underneath. Actually, you could implement the NAND gates in different ways. But I gave you the simplest possible way. And you could also have a timing specification that describes the delay between inputs changing and the outputs responding. How long does it take for the outputs to change after inputs are applied? Okay, so there are types of logic circuits. So combinational logic is what we're going to focus on today. What does this mean? This is memoryless. Basically, outputs are strictly dependent on the combination of input values that are being applied to the circuit right now. You don't have past history. You don't remember anything. You apply some inputs, the combination of them determines what the outputs will be. This is also called combinatorial logic in some books. But later we will learn a different type of logic, which is sequential logic, which is all about memory and storage. This has memory, structure has stored some history, now you can store data values. You can remember. And outputs are determined by previous and current values of inputs. So we're going to leave this for next week. We're going to focus on the combinational part. And we're going to talk about Boolean equations a little bit. So what is a functional specification? This is the specification of outputs in terms of the inputs. So what do I mean by function? Function is really the unique mapping from input values to output values, right? The same input values produce the same output values every time, and there's no memory. That's what combinational is all about. So it's very similar to a mathematical function, actually, without memory. Okay. So we'll look at full one-bit adder. Hopefully by the end of this lecture, we'll see how far we can get. But this is a full one-bit adder. One-bit adder means you add 2 1-bits, binary bits. And this is the, I'm doing this right. I don't know why I'm doing this, but. Is it better? Okay. Maybe not that better. Is it better now? Oh, I think I know what the problem is. It's the, yeah, this is better. I had this problem before. So you need to learn, you need to have some memory. So it cannot just be combinational all the time. You need to have sequential logic. Okay, basically this is, so an adder consists of input 1 bit that you're trying to add and the other bit you're trying to add together and a carry in. So addition is produce a carry, so there's an input carry. And the output is the sum and the carry out. You've all done addition, so there's always a carry in and carry out, right? If you're actually doing it bit by bit or digit by digit. And it turns out the sum is going to be the XOR of A, B, and carry in, and the carry out will be this complicated logic equation. Did you know about this? Who did not know about this? Okay, good. Then you will learn about this. Basically, this is a 1-bit adder, and a 32-bit adder is built by concatenating these adders. That's one way of building a 32-bit adder. So you can see that this is the functional specification, right? The functional specification of this combinational logic is this. S should be the XOR of A, B, C in, and the second output, C out, should be this thing, basically. And what is this thing? AND of A and B, AND of A and C, AND of B and C, and you have an OR. So it's really the OR of bitwise AND of all combination of inputs, right? Okay, and you can think about it. Okay, basically we'll have simple equations first. This is, we're going to be very quick over here. Basically, we've seen already these things, right? This is a NOT gate or NOT function. This is an AND function. This is an OR function. This is not A and B, A or B. And we know how these functions behave. And these are denoted this way. A and B is usually denoted this way, A dot B, or is denoted this way, A plus B. So we're building an algebra. Algebra consists of some operations, right? It consists of elements, it consists of operations. And this was invented by Boole. And if you're really interested, you should read this book from 1847. But I wouldn't recommend it at the moment. Basically, you have an algebra of ones and zeros with and or not operations. What you start with is some axioms. Basically, these are basic things about the objects and operations that you just assume to be true at the start. And you derive some laws and theorems. This allows you to manipulate Boolean expressions. And this allows us to do simplification on Boolean expressions. So what does this mean? Basically, you can have a functional specification, and you can have many, many implementations of it, right? Some implementations may be 1,000,000 gates. Some implementations may be 1,000 gates. So logic minimization or simplification of Boolean expressions are important so that you can minimize the number of gates you use to implement a function. And we will see that. Okay, anyway, you can read that. So okay, let's look at some Boolean algebra. You probably know some of these, but basically there's some, there are 2 elements, 0 and 1. Those are the things that we're going to operate on. This is our alphabet, if you will. So you can compute the closure. Basically, the result of AND and OR always starts in the set you start with. You have commutative laws. Basically, the input order doesn't matter. A or B is equal to B or A. And A and B is equal to B and A. That's commutativity. If you've studied math, you would know that. And there's an identity element, basically. If you do OR with 0, you always get the input. The first input. If you do AND with 1, you always get the input again. And you can distribute. Basically, this is a distributive law. This here, OR distributes over AND, as you can see. A plus B and C is equal to A plus B and A plus C. And when I say plus, it's OR. And the other way around also, AND distributes over OR also. And you can have a complement element. Basically, there's an element that exists if you actually do OR. If you actually input, if you if you OR the input with that element, you get a 1. And there's an element that, this is the identity element for the OR. And there's also an element that exists if you actually do the AND of the input with that element, you get the identity element of AND. This is the basic algebra actually, but it's Boolean. Okay, so there's a duality. Do you know about the duality property of Boolean algebra? Okay, I'll tell you what it is. Basically, all the axioms actually come in dual form. Anything true for an explicit is also true for its dual. Duality is actually very strong. Basically, any derivation you could make that is true can be flipped into the dual form and it stays true. So let's take a look at this, basically. If you want to form the dual of a Boolean expression, you can do it by doing this. Replacing every AND operation with an OR operation, every OR operation with an AND operation, every constant 1 with a 0, and every constant 0 with a 1. But you don't change any of the literals or play with the complement. So let's take a look at that. Basically, this thing at the bottom is the dual of this thing. Basically, I replaced every AND with an OR, every OR with an AND, and this is what I got. And this is correct, actually. If this is true, its dual is also true. And you can check that. Right? It's the distributive law, actually, here. Okay, so let's look at some useful laws. Basically, this x plus 0 is equal to x. X OR 0 is x, clearly. When you OR something with 0, you get the input. But the dual is you replace this one plus with a dot, and you replace 0 with a 1, and you get the correct thing over here. Similarly over here, I mean, I'll let you study some of these. Basically, laws of complementarity is if you OR x with the not x, you get 1. It's clearly true that either x or not x is true, right? That's logic for you. But it's also clearly true that if x is true, not x cannot be true. So you get the dual of this also correct. And the commutative law, again, you can do this also. Okay. Okay, let's do more interesting things maybe. These are the associative laws over here. I mean, it's kind of obvious over here. Distributive laws we've already seen. So let's look at some simplification theorems. So if you have a Boolean equation like this is actually simplified as x, right? X and y, or x and y not. Well, what you get is really x, right? Because you can actually take out the input is independent of the y, right? You get x independent of what y's value is over here. So you can simplify this equation as just x. It turns out this is also, you can test this for yourself by looking at the truth table. X or x and y is equal to x. This actually happens a lot in circuits. And this is another simplification. And this is basically x plus y naught and y, it's equivalent to x times y. So if you know these things, you can actually simplify the logic. But there are other ways of getting this simplified logic, as we will see later on. And these are the duals, basically. Duals are also true. Okay, so basically, these are useful for simplifying the expressions. And it's good to remember some of these, especially this one. It comes a lot in real designs. And this is hopefully obvious, right? Okay, I'm not going to do this for you, but you can take a look at it. Basically, you can prove things with Boolean algebra. How do you prove this? Essentially, using the distributive law over here and the complement over here, that becomes, basically we're simplifying the equation, right? If you distribute, this is what you get. And then y plus y naught becomes 1, because either y or y naught, right? That's true. And you get the identity. Okay. You can do the rest on your own. So this is De Morgan's law. You said that you know it. This is good, but this basically looks like this. And the dual of it is also true. If you do the OR of the inputs and then they're not, it's equivalent to the complement of the inputs ANDed together. And the dual is also true. So basically, let's say we have this function, f equals the OR of A, B, or C, and C. If you apply De Morgan's law, this is what you get. Basically, in logic terms, at least one of A, B, C is true, right? If you think about this logically. This function is saying at least one of A, B, this function is true if and only if at least one of A, B, C is true. De Morgan's law is saying this function is, it's not the case that A, B, C are all false, right? If you write this in language, in human language, that's what you would say over here for the true case. Right? So it's really logical in the end. Okay. So basically, these are conversions are useful when you're converting between different types of logic functions. So why is De Morgan's law useful? You could ask that question, right? It could be useful if you don't have every type of gate in your system, or for some reason, one type of gate is really good, and you've optimized the heck out of it. You designed it really well, and you optimized it, and you want to use it all the time. So you want to convert these equations. For example, let's say your NOR gate is really good. You want to convert everything into an OR gate. That's how you can do it. Apply De Morgan's law, everything becomes an OR gate. Or everything becomes an AND gate. Okay, that's good. I think that's a good place to stop. We're going to pick up here and continue. These slides will be online, so you can study them. Thank you.